This video lesson, we look at the relationship between wave intensity, amplitude, and distance to the source. The intensity of a wave is a measure of the power of the wave. And if that power is spread out over a larger area, that's going to reduce the intensity. So intensity is power per unit area. Here we have a sound wave, and the intensity of the wave near the sound source is much greater than where the listener is residing, which is farther from the source. Increase the amplitude of the wave, and we have a greater intensity at our ears. One-dimensional waves also have wave intensity. So here's a wave in a rope, and we can see its amplitude decreases, and therefore its intensity decreases as you get farther from the source. Here's another wave. We'll decrease that damping, and we'll make the damping 0. So here's a wave whose amplitude doesn't change, so its intensity, or the power per unit area at any point, stays constant. And lastly, here's a wave with much damping, and of course, as it loses energy to the environment, the intensity of the wave decreases. Remember, when particles in elastic medium are displaced from their equilibrium position, and elastic media like water or rope support waves, when those particles are displaced, there's energy stored in the particles, in the wave. And that energy is equal to 1/2 kx squared, where k is the elastic constant and x is the displacement from the equilibrium position. So to get the total energy stored in the wave, we'd have to add up all those particles. But we can see that the total energy is directly proportional to the square of the amplitude of the wave, or E directly proportional to a squared. Remember, x, as I've shown below, is the amplitude a. That means if we double the amplitude of the wave, we're going to get 4 times the intensity of the wave at any given position. Here we are on a sunny day, looking up at the sun. Sun is quite powerful, giving off 4 times 10 to the 26 joules every second, or watts. We're told not to look at the sun, but a light bulb can do more damage than the sun if we stare at it, if the light bulb's close enough. So here we have a light bulb that is 60 watts, a mere fraction of the 4 times 10 to the 26 watts. But if it's close enough to our receivers, our retinas, it can do damage to our eyes. So it's the intensity, the power per unit area that falls on our retinas that's important here. Because we're so far away from the sun, that power per unit area, that power is shared over a much greater area, so the intensity is smaller at the retina. And intensity units are measured in power per unit area, so watts for power per meter squared area. So intensity of a wave depends upon how far away you are from the source. So let's say we have a source S emitting electromagnetic waves, light waves, and we'll say the power of the source is P. We can say the intensity of the light at a distance r from the source is equal to power per unit area. So that's power P divided by that imaginary spherical shell of area 4 pi r squared. So that's the intensity at a distance r from the source, P over 4 pi r squared, where r is the distance to the source. The intensity at a greater distance from the source, capital R, is equal to P, the power of the source, divided by 4 pi capital R squared. So we can see as the distance from the source gets bigger, the denominator gets bigger, and so the intensity gets smaller. So there's an inverse square relationship between intensity and distance from the source. Here we have a light source represented by the red dot at the left, and the rays are moving out towards the right, and we're looking at the intensity of the light at the 2 rectangular sensors marked A and A. Let's mark one sensor a distance d from the source and the other sensor a distance 2d. Let's also say that the intensity at the first detector is I naught. Then the intensity at the second detector is I naught over 4. And at 3D, I naught over 9. And if we go to 4 times the distance from the source, we get I naught over 16. And if we move closer to the source, let's say 1/3 the distance, we'll find the light is more intense here, 9 I naught. And all this because intensity is directly proportional to 1 over the distance squared to the source. Another way to look at this is when that light from that red source hits that imaginary sphere, it's shared over that area A at a distance r from the source. As we move out to a distance of 2r, that same amount of power is now spread out over an area of 4a. At a distance of 3r, that same power is spread out over 9a. That means that the intensity at distance r was I, then the intensity at 3r is I over 9, or 1/9 I. All right, let's review the main points of this video lesson. Firstly, that the energy of a wave, whether it's light or water or sound or a wave in a rope, the energy of the wave is directly proportional to the amplitude of the wave squared. So E directly proportional to amplitude squared. Second point, intensity is defined as the power falling on a unit area. And because power is energy per unit time, then we can also see that intensity is directly proportional to the amplitude squared as well. There's an inverse square relationship between the intensity of a wave and the distance r you are from that wave source. Now we could combine 1, 2, and 3 and we get intensity depends upon the amplitude of the wave and the distance you are from the wave. And in fact, specifically, intensity is directly proportional to the amplitude squared and inversely proportional to the square of the distance from the source. All right, let's try a couple practice problems. First one goes like this. The average sound intensity in Laidlaw Hall when measured at 10 meters from the stage is I naught. Which one of the following gives the average sound intensity at 30 meters from the stage? And we have 4 possibilities here. A, B, C, D. Pause your viewer and try this question. Some of you can do this very quickly. I want to step through the math here. Remember, I is directly proportional to 1 over r squared. We're not changing the amplitude here. And remember, you can always replace that that direct proportionally sign with equals k times. So we've got I r squared equals k. So here's my proportion. I1 r1 squared equals I2 r2 squared. My I1 and r1 is I naught and 10 meters. Substituting in, I get I naught 10 squared equals I, my ladder intensity, times 30 squared. And I solve for I, and I get I, the intensity at 30 meters, equals 1/9 I naught. My answer is C. Practice problem number 2 goes like this. The intensity of a radio signal at a given location is measured as 0.5 watts per meter squared. What will be the new intensity if the amplitude of the transmitted signal is doubled? So here we're at the same location, but the amplitude of the transmitted signal doubled. A, B, C, D. Pause your viewer and try this question. Remember, the energy of the wave is directly proportional to the amplitude of the wave squared. So if it's doubled, then the energy of the new wave is 4 times the original energy. But we want intensity, not energy. Intensity is power per unit area, and since we're at the same location where we're sensing the wave, then there's no change to the area. And we know power is energy per unit time, so in the same amount of time, the power from the new wave is 4 times the power from the old wave. That means that intensity new is 4 times intensity old, and putting in the values, that's 4 times 0.5. Our answer is 2 watts per meter squared.